All right. In the last video, you were exposed to volcanic hotspots a little bit. In this video, we're going to explore these in a little bit more detail. So what exactly is a hotspot? So a hotspot is just part of the mantle that's hotter than the surrounding mantle. And it's hot enough that it can actually burn its way through the crust or melt its way through the crust, creating a volcano. So these hotspots actually stay relatively stationary over long time scales, whereas in your plate tectonics lab, uh, if you didn't know already, you hopefully learned that plates are in fact not stationary. So if you have a stationary object like a hotspot and then a moving plate, um, you'll start to form these volcanic chains. So you have hotspot forms a volcano, the plate moves, that volcano becomes dormant, and you form another volcano over the hotspot, and over a long period of time, you get a chain. You can get a chain of a lot of these volcanoes. We can actually use these chains to infer, well, rather directly calculate the rate of plate motion as a function of time, and then also the direction. So the way that a volcano chain is oriented will tell us, give us information about the direction that the plate was moving, and then also uh, the time in between uh, forming two volcanoes, and their ages allows us to calculate uh, the rate of plate motion. Um, I would highly encourage you to watch the video that I have linked here as well. It's only a minute long, but it does a good job of explaining hotspots, and has some good visuals that I think make it pretty clear how we can infer the direction and speed of plate motion. So there are two notable hotspot chains that we're going to talk about in this lab. So the first being the Yellowstone caldera chain, which we're going to use as an example in this lecture video to show how we can infer direction of plate motion using these chains, and then also calculate the rate of plate motion. So I'll use that and go through an example for an example of some of the questions that you're going to have to answer in the lab quiz. And then in the lab quiz, we'll look at the Hawaiian Emperor Seamount chain, which is a really cool example. So the Hawaiian Emperor Seamount chain has two parts. So it's got the Emperor chain and it's got the Hawaiian chain. The Emperor chain is older than the Hawaiian chain, and these two chains form an approximately 100-degree angle from one another. So they're actually they point in different directions. So, but they're thought to have formed from the same hotspot. So there's some interesting implications about the motion of the Pacific plate, based off of the fact that they're not just one continuous line. There's a distinct change in direction between these two chains. So this picture shows a few of the calderas that are part of the Yellowstone caldera chain. So the hotspot is currently located around the Wyoming Montana border. And then the oldest caldera in this, at least in this image, is the McDermott caldera, which is 17.3 million years old. And so, so these all formed from the same hotspot. So 17.3 million years ago, the McDermott caldera would have been located over the current hotspot. So we can use this information to figure out what direction the plate has been moving. So to do that, you want to look at the oldest feature in a chain and the youngest feature. So in this case, the Yellowstone caldera is the youngest feature. This is located over the current hotspot, or it's currently located over the hotspot, sorry. And then the oldest feature is the McDermott caldera. And so the plate had to have moved southwest. And so you can figure this out by taking the McDermott caldera and trying to trace it back to when it would have been over the hotspot. So, it would have formed here, and then to get to its current location, it had to have moved southwest. So again, these hotspots are stationary over long time scales, whereas the plates aren't. So, assuming that the hotspot hasn't moved, which is very much, which it hasn't, then, we're asking what direction has this plate had to have moved for the McDermott caldera to get to its current location, and that direction is southwest. So you can also think that, remind yourself as you go through the quiz that the plate direction motion moves in the direction of newest to oldest. So what direction is, find the newest volcano or caldera, whatever the newest feature is that's a result of this hotspot, and then find your oldest feature, and then the direction of plate motion points from youngest to oldest. You can also try taking a marker and a piece of paper, put the marker at a spot on the piece of paper, and then move the piece of paper and see which direction you're able to draw a line. You should also, if you don't understand this, please watch that video that I mentioned earlier, and I think that will hopefully help. But yeah, in short, look at some feature that's not over the hotspot currently, that formed some number of millions of years ago, and then ask yourself, what direction did it have to move to get from the hotspot to its current location? All right, so now let's get into some numbers. Let's calculate the rate of plate motion. So here I'm asking, what is the rate that this plate was moving from the formation of the McDermott caldera, from the formation of the McDermott caldera and the formation of the Bernot-Jarbidge caldera. So we can do this by, rate is defined as distance over a time span. So in this case, these two calderas are separated by a distance of 250 kilometers, which, our scientists have gone out and measured, but you could also do that very easily. Or if you're able to locate these two calderas on Google Earth, you can use that as a tool to measure these distances. But yeah, in short, they're located approximately 250 kilometers apart from one another. And the McDermott caldera formed at 17.3 million years ago. The Bernot-Jarbidge caldera is younger and formed at 2.5 million years ago. So there's a difference in time of 4.8 million years. And again, the hotspot would not have moved during this time. Instead, it would have been the plate. So basically, from the formation of the McDermott caldera to the formation of the Bernot-Jarbidge caldera, the plate would have had to have moved 250 kilometers, and it would have taken 4.8 million years to do so. I'm not going to go through all the math in detail, but you should spend a little bit of time looking through these steps because you'll have to go through these steps and the lab quiz. But basically, you'll convert 250 kilometers into centimeters and the 4.8 million years into just years, and you get a rate of travel for this plate of 5.2 centimeters per year. Now let's look at two other calderas. Well, the one new caldera. So here I'm asking, what was the average rate of plate motion between the formation of the Brno-Jarbidge caldera and the Yellowstone caldera? So again, these two calderas are located 475 kilometers apart. However, the Brno-Jarbidge caldera is 2.5 million years old, and the Yellowstone caldera is approximately 0 million years old. Obviously, it's slightly older than that, but on this time scale, it's very young and effectively 0 million years old. So they are separated in distance by 475 kilometers and separated in time by 12.5 million years. And so that gives a rate of 3.8 centimeters per year. So that begs the question, has the North American plate speed increased or decreased as a function of time? So as we calculated between the formation of the McDermott caldera and the Brno-Jarbidge caldera, the plate was moving at 5.2 centimeters per year. And then between the Brno-Jarbidge caldera formation and the Yellowstone caldera formation, the plate was moving at 3.8 centimeters per year. So therefore, this plate speed has actually decreased. So, the plates don't actually move at a constant speed, or the speed at which they move actually changes as a function of time. And you can use these, hotspot chains to map out how quickly they are moving and how this changes with time, and then also how the direction changes with time, which you'll explore when you look at the Hawaiian Emperor seamount chain during your quiz. So I understand this is an extremely useful topic for earth scientists, but if you've never dealt with anything like this before, I understand that it can be a complicated topic, and there's a lot to take in. So if you're confused, I strongly encourage you to attend my office hours this coming Wednesday, and we can step through this in a little bit more detail, and then we can also work through the math together. So yeah, if you have questions or you're a little bit confused, please come to my office hours or reach out to me, and we can set up separate office hours by appointment.